Okay, let's go ahead and start the class. Today we are going to talk about the exam. We are going to only focus on the exam. We will talk about the exam policies. I will answer your questions you may have, the questions you may have about the exam, and then we will solve some example problems specifically from chapter 3. I'm not sure if you have seen the previous lecture, but on Thursday, we didn't have an in-class instruction because I couldn't come in, but I uploaded the solutions to homework 1 and homework 2, essentially, right? I solved all of them, all of the questions for you. So hopefully you have seen those lectures, that lecture and those solutions, and we will go over some example problems from chapter 3. And let's actually talk about this first. I will upload homework 3 tonight, right? But it will be due next week, which means that it will be due March 16th. Okay, next week to homework 3 will be only focusing on the material from chapter 3, Bernoulli's equation. Okay, but since you need this material for your exam, what I'm going to do is that I'm going to post a solution to this homework tomorrow at 5 p.m. So, okay. So whoever submits their homework before this time will get the homework points, and then we'll get an additional homework as bonus point, right? You will get, I think every homework is worth 4% of your total grade. If you submit before Wednesday 5 p.m., tomorrow 5 p.m., you will get an extra 4% added to your final grade, okay? But if not, you already have the solution. By the due date, you can just copy and paste from the solutions and get the points, okay? Does this make sense? Is this clear? Okay. So this is for the homework. For the exam is going to be on Thursday, as you know, hopefully by now, from 2:50 p.m. to 4:05 p.m., so 75 minutes. We will have 10 descriptive or short answer problems, okay? What do I mean by descriptive problems? For example, I may ask you to tell me what the center of pressure is. I think I told you this, but what the center of pressure is, right? Or I may ask you to give me the equation for capillary force. Just the equation, right? But what I mean by the short answer part of it is that I may ask you to find the dimensions. So I give you a random equation, and it has a constant in it. I may ask you to find the dimensions for that constant. As long as you know the dimension for the other parameters that are involved, like pressure, force, whatever, right? You should be able to find the dimension for that constant easily, right? Finding the dimensions. So short answer problem. So essentially only problems that involve only one equation, which is usually given to you, just plug and chug, right? As long as, like for this, yes.
So subjects for this test are like chapters 1 through 3?
That's a good point. So I wanted to include the half of chapter 4 we covered on last week, but I decided not to. So this test will only be from chapters 1 to 3. Okay. We are having an online question for the question. Okay, so we will talk about it. We had an online question. So 10 descriptive short answer problems, and then 3 longer problems. 3 regular normal questions. Let's call them normal problems. This is the problem that, for example, I ask you to find the pressure difference between the 2 points in a pipe, right? The hydrostatic equation. Or I will ask you to apply the Bernoulli's equation to something, right? 2 of these problems will be very straightforward, and you should be able to handle those as long as you know the material, as long as you have reviewed the homework. You should be able to find the answer for them very easily, hopefully. But one problem will be a little. I don't want to say it is hard. I just want to say so 2 normal problems, and 1 will be a creative problem. Let's call it a creative problem. So you will need to be able to think out of the box a little bit. I will solve an example of these type of problems as well today. Okay, so 10 descriptive problems, 2 normal problems, 1 creative problem, and it will be a total of 100 points. Is there any questions about the problems?
How many points is each short answer on that?
Short answer, I haven't finalized. I haven't decided yet, but between 2 and 4. So you probably will get like 30 to 40% of your final total grade out of these 10 problems. Okay. And I'm thinking like 40% of these and 20% of out of those 3. Right? So although this one problem is a little harder, but it will have the same weight. Right? So if you want to get an A, you should be able to solve that problem. At least you should be able to attack the problem, like have some sort of an idea. Okay, any questions? Any other questions? Yes.
How much work are you looking for in the normal and creative problem?
I didn't hear.
How much work are you looking for in the normal and creative problems?
I don't know. That's a very hard question to answer.
It's just simply, is it fine if we sometimes like skip substitution steps but still gets the answer? Just like we have the right equation, we have the variables defined, we just don't do substitute variables with.
Yeah, that should be. It really depends on how you like answer the problem. But as long as you have the correct equation and you tell me that these are the variables I want to plug in and this is the final answer, I will accept your solution. I will accept that type of problem solving to any solution of the problem. I don't know how my grader has been grading your homework though, so that's his choice. Okay, any other questions? Let me see if you have any online questions. Let's see. Can we put whatever the equations in? So, is it we have one question here about the problems. Is it purely going to be theory finding dimensions, or are they going to be more in depth as well? I don't know what you mean by that question, but again, descriptive problems are very theoretical, conceptual. Like, tell me what the capillary pressure is. Tell me, like, where do we get the Bernoulli's equation, right? It is based on the principle of Newton's second law, right? Conservation of momentum equation, right? Any of those answers will be acceptable. But in depth, I may like ask you to, like, what will happen to pressure at this point if I increase the velocity. You don't have to give me an answer. You just have to tell me that it will increase or decrease. So it will show me that you understand the concept, right? And for the short answer problems, again, like finding the dimension, or what else? Like very one line, like very small problems that you need to do, like convert these units to the other unit, right? These type of problems, yes. I haven't finalized it yet, but up to 40 points, okay, total. So 4 points each. Okay. Any of the Quizlets? So we have a question about whether you can. I haven't seen any Quizlets for this course. I usually use the book and my own lecture notes. So I don't know if I can recommend any Quizlets for this specific course. But I will make sure that I'll upload the final version of the lecture note that I think I haven't uploaded after chapter 2. I will also make sure to upload the solutions to the homework, so you can use the lecture notes if you want. I will also upload a PDF review of the concept.
Says that we can have a two-sided sheet of paper.
We will talk about it.
Okay.
We will talk about it. So if there is no other questions about the problems, let's talk about the policy, exam policy. So exam, you are allowed to bring a two-sided equation sheet to the exam, right? You can write whatever you want to write in the equation sheet. They can be as small as you want it to be, or as big as you want. As long as it is a letter size sheet, you should be fine, okay? And you should not include any solutions in your equation sheet, okay? And you should submit your solution. You must submit your equation sheet. Let me write this down on the board. So two-sided letter size equation sheet. Cheat sheet. Let's call it cheat sheet. Because you can actually, if you want to, you can write the concepts and definitions on it as well. As long as it doesn't have any solutions to any of the homework problems or anything, okay, that we have solved in class or the homework. So, and you have to submit it with your exam. Submit it with the exam. With your name on it and everything. Okay? Again, exam is 75 minutes. There are some people who have registered for STRC. I think I'm using the correct abbreviation. And they need time and a half. Printer, essentially letter size paper is printer size paper, right? The regular printer size paper. Yeah, printer paper. And your exam time is 75 minutes. There are some people who have registered with STRC. They're going to get time and a half. I was thinking of putting on all of the people who have already registered with STRC in another room, in the conference room we have here. But I think because of privacy issues, it's better not to do that. So all of you come to class and sit here. I have a list of people who can have time and a half, right? If you are among those people, you can sit and use your extra time. If not, then you have to submit your exam with everyone else in the class, right? And of course, I have the list, so it's not like you can just not register with STRC and get the time and a half. If you have any issues, if you need more time, and if you have not had the time to register with the STRC, you can send me an email. We will work out something. And since there is no class after this, after hours, it is probable for us to extend the time for everyone in the class. But if that is the case, if I extend the time for everyone to 90 minutes or 100 minutes, then the STRC people still get, if that exam time becomes 100 minutes, people who have registered with STRC will get 150 minutes, okay? So the total exam time will be extended for everyone. For STRC people, it will be multiplied by 1.5. Yes?
One question.
Sure.
So on the test, are we going to be doing, say, conversions, for example? Like, say, going from imperial to metric units?
No.
So given each question, just stay within that set of units?
That's you may need to do some conversion for the short answer part, but that will be the purpose of the question.
Well,
Okay.
So just keep like some reliable measurements, like a meter to a foot. Okay, just set some constants like a length conversion, time conversion, mass conversion. Okay.
Yeah, it is probably a good idea to have those on your equation sheet for the short answer problems, but you're not going to need to convert anything in the normal problems and this like harder problem. And usually, what happens is if you forgot to include an equation or a conversion, you can ask me. I'll be right on the board for everyone. Okay. My TA will also be here. For the time and a half people, I will leave, and my TL will stay with you. My grader, not you, will stay with you to answer your questions if you have any. But I assume at that point of the exam, everyone already has a good idea if they can, and they know if they can solve the problems or not. So me not being here after the exam won't cause any problem for anyone. And what else? Yeah. So 75 minutes. Let's see if you're missing anything. If you're the exam will be in class, so all of you must come to class. There won't be any online option for the exam. So if you are watching this online, there are a couple of people who are already watching this online. You have to come to class. So I have one question from the people who are watching online. Is they are saying that I know you said we can't have solutions, but can we have written on there how to derive certain equations? So can you include derivations? Yeah, you definitely can include derivations, but I don't see how that would be useful, because I may ask you one of these problems can be a parametric problem, meaning that I will give you the velocity is v instead of a number, like and you just plug in that letter instead of the number in the equation and give me a final value. That is not a derivation. I'm not going to ask you to derive the Bernoulli's equation in the exam. So you can definitely include the derivations if you want to in the equation sheet, but I don't see how that would be helpful. Okay, if there's no other questions about the exam policy and how the exam is conducted, let's get to the problems that we want to solve. I'm going to start from the creative problem that I'm going to give you. So this is again, as I said, this doesn't have to be, it is not a hard problem. The only part that may be a little harder is the start of the problem. So when you figure that out, then the rest of it should be easy. You should be able to handle the rest of it. Okay. And some part of this problem is actually does include chapter 4 that we talked about. I'm just going to give you the solution for future reference. You may have it in there, but the first part of it is from the 3 chapters, the first 2 chapters. So We are told to consider a one-dimensional motion of fluid particle moving on the certain line of a converging channel. So we have a converging channel. And there is a fluid particle moving on the certain line, center line of this converging channel, as shown in the figure. The vertical dimension of the channel varies, right? So this dimension changes. It goes from h, and this is h as well, to h over 2. And we also have the equation of this variation. So the equation of this line. The equation of this line is going to be y. This is the axis y, x is equals to h minus, and that this h is given. Can be 1 meter, 2 meter, whatever. H over 2 sine of pi x over 2L. L is the length of the channel. These are also given. So this is an example of the parametric problem that I told you. H and L are not variables. They are constants, right? But you don't have a number for them. This is not a derivation. It's just a parametric problem. OK, this is h over 2. We have the equation of this line, right? And we want to assume that the flow is steady, incompressible, and inviscid. Use the conservation principles to describe the velocity along the channel center line. So we are told to use, this is kind of a hint, we are told to use the conservation of mass to find the velocity at the center line. So velocity here. It's a one-dimensional velocity, so velocity starts from 0, then it changes until it gets to here. Velocity is a function of the location you're at, the x location, right? So we want to find the velocity as a function of x. OK. First, look at this problem. We don't know what to do. I mean, there are probably some people who do know what to do, but it looks like an unsolvable problem. But whenever you see these type of problems, you essentially have to write the conservation of mass equation between two arbitrary points, right? And that will give you the solution you are looking for. That's the only part you should understand. Other than that, it will be a streamlined problem, a regular problem. So let's see what I mean. First, what is the conservation of mass? Incompressible steady inviscid. Conservation of mass told us A1.V1 is equals to A2.V2. Or a more general term, A.V, area multiplied by velocity, is constant between each 2 points on the streamline. Is going to remain constant. So, and this A here is the cross-sectional area. So this is the area that you're looking at. What is this area? That's the first thing you want to find. This area is going to be this length multiplied by the depth of the channel. Okay? We're going to make everything simple here, simpler when it comes to calculations, and we are going to assume that it has a unit depth. So your area is going to be this length multiplied by this unit depth. That's the cross-sectional area. multiplied by the velocity at that specific point. Okay, at point 1, I think we are given the velocity at point 1. Yeah, 2 meters per second. Let's keep it. Let's say it's v infinity. Okay, so as long as you have the velocity and the area of 2 locations, you should be able to, or as long as you have 3 of these 4 parameters, you should be able to find the 4th one. Well, how can we find how velocity changes with x? Again, I choose an arbitrary point anywhere. And it is x meters away from x equals to 0, right? So we have x here. We have x equals to 0. Let's do that. Let's call this point a star, right? So, and then the starting point is point 1. So A1 V1 is equals to area at that arbitrary star location multiplied by V star. Okay? What is A1? A1 is this length multiplied by 1. So 2h. H multiplied by 1 is 2h. What is the velocity there? V infinity. Then the next part, for the right-hand side of the equation, we have to find the area at this arbitrary location, right? How can we find that area? Yes.
2h minus x, or is it just an h minus x? And there's
Why would it be h minus x though? What would be the area? So area here is going to be this length multiplied by your depth, right? It's a unit depth. This length is 2y, right? Y. So 2y, right? We don't know what that y is, but we already know it is y, right?
is this a cylindrical area, or is this a?
So we are assuming it's a rectangular cross section, right?
Okay.
This length multiplied by a unit.
Okay, so we're doing.
If you were told it's cylindrical, then you had to do a cylindrical cross section. Yeah. So what will be the area at this location as a star location? It will be this length multiplied by 1, right? That's a unit depth. It doesn't change. And we are told to keep that constant. What is this length? We have the equation of the line, right? So we already know what is this y. Just have to multiply it by 2, right? And then multiply it by your depth, which is 1, right? So multiply that equation by 2. 2h minus h sine of pi x over 2l multiplied by your v star. Okay, so let's take a look at this equation. We already know h, right? We are told it's a constant, and we are given a number here, but we already know that parameter. That doesn't change. We already know v infinity. Same is true here. The only parameter we don't know, and it's an arbitrary choice, is x and v star. So if we rearrange this equation, we are going to find velocity as function of x. Does this make sense? So we have the equation of velocity as a function of x. So based on that equation, we should be able to find the center line velocity at any location. And let's assume your h is 1 meters, L is 1 meters as well. V infinity is 2 meters per second. And let's plug all of those numbers in to simplify the equation. So center line velocity is going to be 4 divided by 2 minus sine of pi over 2x. See, that arbitrary location, just choosing an arbitrary location x, helped us find the equation for velocity. Does this make sense? Yes? No? Yes?
I'm just asking, so why is V1 like V infinity in this case?
Just wrote a number. It can be any. The point was v here is given, right? It's just constant value. But in general, it's a free stream that is coming in, right? So velocity of free stream, we usually use V infinity for it. Okay. Do we have any questions here? Good. So this is the type of C. This problem is not a hard problem. Conservation of mass. Hopefully, you know what conservation of mass is. At least you will know by the exam time, right? The only thing that you really needed to figure out was the choice of this arbitrary point, right? Anywhere would have been fine except for the locations you know the values for, right? L and 0, right? Other than that, any location would have been fine, and you have the equation of velocity. Then the next part, if there's no other questions, we can actually move to the next part, which is, I'm not sure if it was part of chapter 4. That's why I'm solving it. I have to go back and check. So if this part was the second part of the problem is a part of chapter 4, then it won't be in this exam. But if it wasn't, I have to go back and check my lecture notes. But if it wasn't, you will get something like this in the exam as well. The next part, we are asked to find the acceleration. Okay. We define acceleration of a fluid particle as the total derivative of velocity with respect to time. What does this mean? Is that we are going to get the changes of velocity with respect to time plus velocity in the x direction if you are in the Cartesian coordinates direction multiplied by the changes of velocity in the x direction, velocity in the y direction multiplied by changes of velocity in the y direction, and then velocity in the z direction multiplied by the changes of velocity in the z direction. We are told that it is a steady state case, so there is no change. There is no local changes to velocity. Changes with time is going to go to 0. It's also a one-dimensional case, so your acceleration is going to be equal to u partial x. We have that equation for u. This is, since it's a one-dimensional case, it will be u. Just plug that in here for the first term. And for the second one, you take the derivative to find the acceleration equation. Okay. Any questions? Okay. Let's start working on another problem. Let me just check to see if there's any. Okay, so another problem, we are told at a given point on a horizontal streamline in flowing air, the static pressure is negative 2 psi. Okay, and the velocity is 150 feet per second. We want to determine the pressure at a stagnation point on the streamline. So we have a one-dimensional streamline that is going to hit a cylinder, right? A horizontal streamline. We want to find the pressure at a stagnation point. The first thing you need to know here is what is a stagnation point, right? If you recall from the dynamic pressure and static pressure discussions we have had, a stagnation point is a point where the velocity is 0, okay? And which essentially is going to be this point, point 2. So V is 0, a stagnation point. So V at point 2 is going to be 0. We are given the V at point 1 and P at point 1. Also, something that you may notice here is that we are getting negative pressure. How can we get negative pressure? If you recall, we are usually dealing with gauge pressure, unless we are told otherwise, right? So gauge pressure is assumed that your atmospheric pressure is 0, right? Which is not 0. So a negative pressure is essentially telling you that your pressure is smaller than the atmospheric pressure, okay? That's a negative gauge pressure. But a negative absolute pressure is cannot happen. Okay. So let's write the most general form of Bernoulli's equation. P1 plus 1/2 rho V squared, rho V1 squared plus GZ, right? Rho GZ or gamma Z. That's rho G equals to P2 plus 1/2 rho V2 squared plus gamma Z2 on the streamline, along the streamline. It's a horizontal streamline. So what does this tell us? This tells us that Z does not change. This is Z2. So these parts will cancel out. Okay? And we figured out that the velocity at point 2 is 0. So eventually, your equation will become P1 plus 1/2 rho V squared 2 equals to P2. P1, negative 2 psi. Rho, let me check the rho. You will be given the rho, so you don't need to calculate this yourself. Let me see what the rho is here. Is 0.00238 slug per cubic feet, right? And the velocity is 150. So if you plug these numbers in and give me a pressure, you won't get any points. You will get some partial credit, but you won't get all of the credit. Why is that?
The density is not in pounds.
You don't need to convert the density, right? What you need to convert is your PSI to PSF.
Yes.
Okay. As long as you have PSF here Everything else is consistent. Okay? So we have to, these type of conversions you will get, but we are within the British units, right? So you are not changing from SI to British. We have to change PSI to PSF, right? How do we do that? How do we change PSI to PSF, or pounds per inch squared to pounds per feet squared? Multiply it by 144, right? Why do we multiply it by 144? Every feet is 12 inch, right? Every inch squared, every feet squared is 144 inches squared, right? 12 to the power 2, yes.
Can you use calculators on the exam?
Yeah, sure, definitely. Yeah, that's why. Yeah, definitely. You definitely can use calculators on the exam, right? Yeah, you cannot calculate this by hand. I don't expect you. Yeah, don't worry about it. And okay, any questions? So you plug in the numbers, you just multiply that by 144. And let me give you a final answer. So your P2 is going to be equals to negative 1.81 PSI. You can convert it back to PSI. Okay. Any questions? So something that I'm reminded here is that in your an example of a descriptive problem is the definition of a stagnation point, right? What is a stagnation point? Or what is the difference between the stagnation pressure and the static pressure? Or what is the dynamic pressure? What's the definition of the dynamic pressure? All of these things that we have discussed, right? Who can tell me what's the difference between a static and dynamic pressure?
Static pressure is pressure at a static point, and then like dynamic pressure should be pressure in motion. Because it should be in moving.
So let's actually talk about this since we are. We have a static pressure, which is the pressure you are going to feel if you move with the particles themselves, right? So essentially, if I'm not moving, I'm gonna feel 1 atmosphere, right? That's gonna be the static pressure inside this room, okay? Then we have the stagnation pressure, which is the pressure your fluid particles are gonna feel if you bring down their velocity to 0 isentropically, okay? And that isentropically, that type of process is very important here, okay? And then the difference between the two is going to be the kinetic energy, right? You're removing all of the kinetic energy from the system. You're bringing down the velocity, the maximum kinetic energy, to 0, the lowest kinetic energy. So the difference between these two is defined as dynamic pressure, which is essentially the kinetic energy of your system, or 1/2 rho v infinity, or rho v squared. It's called just rho v squared. And we're going to use Q for it. Okay? So these are different examples of descriptive problem or one-liner problem. Okay? Or for a short answer problem, I may give you the stagnation pressure and the velocity and ask you to find a static pressure, right? Just plug in the number there. It's a very simple calculation. As long as you understand the concepts, you should be able to find that answer in less than a minute. Okay? Okay. So another type of problem we are going to get is this. And this may have the most calculation involved, but it is not the hardest problem, right? You just have to make sure that you are careful when you are doing the calculations, because you have to do a lot of plug and chugs, right? So we are given a pedostatic tube that is used to measure the velocity of the helium in a pipe. You have this type of pipe, okay? And this is a pedostatic tube. This part of it is going to be able to measure the static pressure, and this part of it is going to be able to measure the stagnation pressure, right? Because when the fluid particles go inside, the velocity becomes 0. But here, we are not going to decrease the velocity at all, right? In theory. This is point 1. This is point 2. And we are given the temperature and pressure, 40 degrees Fahrenheit, 25 psi. A water manometer connected to the pedostatic tube indicates a reading of 23 inches. So we have water here. And this height here is 23 inches. Okay, we want to determine the helium velocity. Is it reasonable to, that this part of this problem is something that I think we mentioned very briefly, but it is possible to get something like this on the exam as well. The calculations of it is not that hard, but as long as you know the criteria. Okay, is it reasonable to consider the flow an incompressible flow? Okay, that's the last part. So first part, what is the velocity of helium? Second part, incompressible assumption. Is it correct or not? Okay. For the velocity part, it's pretty straightforward. We essentially have to write the Bernoulli equation between point 1 and point 2, right? The idea was this part, when the fluid particles go inside there, their velocity is going to reduce to 0. So this is a stagnation point. Whereas here, their velocity is not going to change. That's the idea of the pedostatic tube. This part of it is the pedo tube, which will measure the stagnation pressure. This part of it is the static tube, which will measure the static pressure. So let's write the Bernoulli's equation between these two parts. P1 plus 1 half rho v squared, rho 1 squared, plus gz1 rho gz1 equals to P2 or gamma. Just same thing. P2 1 half rho v2 squared, rho gz2. There is no height difference, so this will cancel out. Again, the idea here is that point 2 is a stagnation point, right? So velocity 0. Okay, and P1 minus P2, I'm going to move P to the other side, is going to be equal to 1 half rho V1 squared, which is the helium velocity, right? Well, how can we find P1 and P2, or the pressure difference between the two? How can we find that? Yes.
That P1 is 25 psi, okay? We can gauge pressure, we can find P2. Using just rearranging it to find what P2 is, and then we can just find P1 minus P2. Oh,
okay.
Actually, we already know the difference because it's V1.
We already have the difference from this tube, right? The difference here, difference between these two pressures is going to be equal to gamma multiplied by this height, right? That was the idea of the hydrostatic pressure, right? So P1 minus P2 is going to be equal to gamma of water height multiplied by the height. That's actually negative, right? Because it is going to decrease. Okay. So we have the gamma of water. It is usually given to us in a British system. Gamma of water is 62.4. We have the H, 23 inches. The only thing that we have to be careful about is that gamma of water is given to us as feet per pounds per feet, cubic feet. Okay, but height is in inches. So you have to convert either the inch to the feet or gamma to pounds per inch squared. Okay, plug those numbers in, and you will be able to find the pressure difference. Okay, so this part of it we already have. What about the density? So it is possible for us. I mean, it is possible that I don't give you the density, and I ask you to find the density of the helium. How would you go about finding the density of a gas?
Gamma divided by gravity. Because gamma is equal to rho times gravity, wouldn't it just be rho equals gamma divided by?
Well, we don't have the gamma of helium. We have the gamma of water, right? Here, that's a very good point actually. Here,
Don't we have the specific gravity right now?
we don't have the specific gravity, no. But before moving on, Brandon, right? Brandon brought up a very good point here. This density here is helium's density, right? We are writing the Bernoulli's equation between 0.1 and 0.2, which contains only helium, right? Inside this tube, though, we have water. So this gamma, which is going to give us the pressure difference between 2 points inside the helium, is gamma of water, right? Make sure not to confuse it. But one thing we can use, since we are given the pressure, we are given the temperature. Whenever you have the temperature and a pressure, that essentially that's a.
Could you try?
I didn't say Siri. Yeah, whenever you have the pressure and temperature, that's actually a hint to ideal gas law if you're dealing with a gas. So what was the ideal gas law? P equals to rho RT. I will definitely give you the R for helium in this specific case. We have the temperature. The only thing that you have to be careful about here is to convert Fahrenheit to Rankine, right? We have the pressure as PSI, and we should be able to find density. Just have to be consistent in units, right? If you're dealing with feet, deal with feet all over. If you're dealing with inches, deal with inches all over, right? So if one of them, like PSI, is going to be in inches, right? But your R is usually given to you in feet, right? You have to make sure that those two units are consistent. And then you find the density, which eventually means that you will be able to find the velocity of helium. But then we need to get to answer the second part of the question. Is the incompressible flow assumption a correct assumption? How can we answer this problem? If you recall, we had a very brief discussion about compressibility and incompressible assumption. The idea was that there is no incompressible fluid, right? Incompressible fluids in general are an ideal type of fluid that are not there, that are not out there in the void, right? So every fluid is compressible to some degree, right? But we chose an arbitrary point, right? We said if the changes in density, right, or volume of a fluid is less than some degree, right? In this book, we said 3%, right? So if you apply pressure, changes in density is less than 3%, then you can safely assume your pressure, your fluid flow is incompressible, okay? But how would we don't have any idea about the changes in volume or density, right? How would we determine that here? What we eventually did was we defined this Mach number, right? As, which is very common in aerodynamics, right? As your velocity divided by a, which is the speed of sound, right? And we said we can calculate the speed of sound as the square root of kRt, right? K here is 1.4. In most textbooks, you're going to see a square root of gamma RT, but here they're going to use K, not to confuse it with this gamma here, right? That's just your Cp divided by Cv for air, which hopefully you remember from your physics and chemistry. Okay, so do we have R? Yes. Do we have T, temperature? Yes. Do we have K? Yes. We can find the speed of sound for this specific case, right? But how does that relate to the compressibility? If you recall, after we made that, we decided on that arbitrary point, we did some calculations and ended up seeing that if Mach number is smaller than 0.3, then we can safely assume the flow is incompressible, right? Here we have already in the part 1, since we are already using the Bernoulli's equation, we already have assumed the flow is incompressible, and we have found the velocity, right? So next step would be to find the speed of sound, plug in the velocity, and the velocity we're going to have here is 203 feet per second. A speed of sound, after you plug in all of the numbers, the speed of sound is going to be equal to 3,210 feet per second for helium. This is for helium at this specific temperature, which essentially means that your Mach number is going to be equals to 0.063. This is much smaller than 0.3. So the incompressible assumption was the correct assumption. Okay. Is there any questions? Yes.
Velocity 203 feet per second. That was from problem.
That was from yes. So if you plug in all of the numbers for this velocity, you should get 203 feet per second. Okay. And that was the part B of the same problem that we solved. This is some, yes. Oh, that's it. Is there any other questions? Okay. This is something you will probably get in the exam, right? It may be, the exam problem may involve more tubes here, which essentially means that you have to add more terms here, right? So it won't be that much more complicated. It just has a little more computation, right? Just have to do some more computation. Okay. Any questions? No. So let's solve one more problem, and then let's solve this one. Let's solve this one. This problem is telling us that water flows from the faucet of the first floor of the building. So this is, let's say this is your wall, second floor, first floor, and the basement, right? And this is where the the ground is. We have your faucet here for the first floor, and we have piping. This is a faucet in the basement, and this is a faucet in the second floor. Okay, and the water pipes are connected on the ground, right? Each floor is 12 feet high, and the maximum velocity of the faucet in the first floor is going to be equal to 20 feet per second. Okay. We want to determine, we are given all of these dimensions too. Let me give you. So 4 feet, then again 4 feet. Again, we have 4 feet here. We are told that this is a steady, inviscid, incompressible flow, which is telling us that the Bernoulli equation applies. And we want to determine the maximum water velocity from the basement faucet and from the faucet on the second floor. So let's call this point 0. Let's call this point 1 and point 2. What we essentially need to do is to write the Bernoulli's equation between all of these 3 points. Okay. Let's do point 0 and 1 first. So P0 plus 1/2 rho V0 infinity V0 squared plus P1 equals to P1 plus gamma Z1 or rho GZ1 equals to P1 plus 1/2 rho V1 squared plus gamma, that's Z0 here, Z1. Okay. We are not told anything about the pressures other than the fact that these are faucets, right? What essentially a faucet is a free jet, right? And the condition for a free jet, if you recall, was that its pressure is equals to atmospheric pressure, or the gauge for the gauge pressure, as we can say, its gauge pressure is 0, right? So pressure is going to be 0 here when the water comes out of the faucet. It's going to be 0 here, and it's going to be 0 here, right? So we can essentially remove the pressures. What about the z's? Gamma Z0, gamma Z1. We can move them to one side of the equation and have their difference present. So gamma Z0 minus gamma Z1, right? What is the height difference between the two? Is 12 feet, right? So 1/2 rho V0 squared plus gamma, let's move it to the other side. 1/2 rho V1 squared plus gamma multiplied by, or 12 multiplied by gamma. Okay? So we are given the density, we are given the gamma for water. Just plug in the numbers, you find the velocity at the basement, velocity of the faucet at the basement. You do the same analysis, you will find the velocity of the faucet at the second floor, which essentially is going to give you the same equation. The only difference would be the sign here. So for the second one, we are going to get rho second floor, rho V1 minus 12, because this one is higher, right, instead of lower. Is there any questions? No? Yes.
Just make sure, why is the second equation have a negative 12 for height?
Because this is 12, this one is 12 feet below, right? So whatever, let's say
Okay, so
the base height, yeah. So if I move this to the other side, the height of this one is 12 feet higher, which means positive gamma. But for the other one, this is 12 feet lower, right? Does it make sense? Okay. So if there is no question, I'm just going to give you some examples of the descriptive problems you may get, right? Some more examples. One thing that you may get is the definition of a fluid. What is the definition of a fluid? The main, whenever you want to define a fluid, you have to talk about the main difference it has with a solid, right? The idea was if you apply shear stress to a solid, it will resist that shear stress. But the fluid cannot resist the shear stress, and it will move continuously, right? Which doesn't happen for a solid. Okay? So in layers are going to move. Another example is to definition of the no-slip condition. Hopefully you know what a no-slip condition is. Let's see. No slip. So no slip condition usually is a condition at the walls, in case you don't know, right? At the walls of the fluid, right? And the idea here is that the fluid, you can actually understand it from the name. The fluid layer adjacent to the wall cannot slip on the wall. So it will stick to the wall. It will get stuck there. What does it mean? It means that the velocity of the layer adjacent, fluid layer adjacent to the wall is going to be zero. Or in simpler term, no slip condition means that the velocity of the fluid at the wall is zero. Okay? And like one thing that I may ask you is to give me the shear stress equation in a fluid, right? How can we find the shear stress at the wall in a fluid, right? Which, if you recall, was mu multiplied by partial u partial y, right? Okay. We have talked about vapor pressure as well and cavitation. We have had a very small discussion on that. Just some conceptual things. Surface tension is another important part. These are all chapter 1 capillary effects. And then we actually talked about the gauge pressure, absolute pressure, all of those things. Let's see. But hydrostatic pressure variations with height, with elevation. It's a very important part of the this exam, right? The hydrostatic forces, hydrostatic pressure, all of those equations. And let's see. Buoyancy and stability. This is something that we talked. We didn't solve any problems from it because it is not a very hard concept to handle. But you will probably get a descriptive problem out of a stability part of it, right? If you recall, we talked about the center of gravity. We talked about the centroid of the problem, a centroid of an object immersed in a fluid. So you just should tell me what is the relationship between the stability and the location of center of gravity and centroid. Where does the buoyancy? Where do we apply the buoyancy? Where do we apply, or where the buoyancy is exerted on the immersed body, where the weight is exerted on, which is the center of gravity. And we talked about the dynamic pressure and the gauge pressure. Maybe like, I guess that's it. Yeah. I think the acceleration part, I'm pretty sure the acceleration part I solved in the beginning of the class was part of the chapter 4. Yeah, it's definitely part of the chapter 4. So the acceleration part of that problem won't be part of the exam, but the rest of it will be. So is there any questions? Yes.
I just want to confirm with everybody coming to class, if there's people that are positive for COVID and are quarantining or self-isolating, are they required to come in class, or will you have an alternative method for them?
Of course, if you have to quarantine, if you have COVID, we don't want you to come into class. And you just have to submit a positive test result to me, and then we'll go from there. That will be on an individual basis, okay? I probably won't do. So for people, it is not a set policy. I have to think about it. Thanks for that question, actually.
Because I know that there are some people that are positive in our class right now that are watching online. So I just wanted to make sure for them that they knew what you were doing.
Okay, so yeah, thanks for bringing that up. I didn't know that. I haven't received any recent emails about the positive COVID situation. So if you are COVID positive, right, don't come to class, right? Not only you shouldn't come to class, not only you don't need to come to class, you shouldn't come to class, right? And send me an email with your positive results, and then we'll set an arrangement. What I'm thinking right now is to drop the exam 1 for you, and then use your exam 2 grade as the exam 1 grade, right? I think that's something you can definitely do. But yeah, send me an email, right? If you don't send me an email and tell me after the fact that I had COVID, that will complicate the matter, right? We will definitely work with you, man. I will definitely work with you. Okay, hopefully you feel confident enough for the exam. I hope you all will get A's, good grades, and ace the exam. See you on Thursday. And don't forget about the homework. I guess that's it.